Shall we get started? Okay. Now listen.
Yes, sir.
Right. So the next topic that we are going to see is called as Ampere's circuital law. Okay. So if you observe this Ampere's circuital law, this is somewhat similar to the concept of Gauss law that we applied in electrostatics. So what did this Gauss law state? It said that the surface integral of E dot dA is equal to the charge enclosed divided by epsilon naught. You remember this? Right. In a similar way, this Ampere's circuital law is used wherever there is symmetry. Right. See, generally, when you take any of these chapters where you need to calculate fields, basically you will have two laws associated in that chapter. Okay. So basically you will have two laws. Like if you take the first chapter, to calculate the force between two charges, we had Coulomb's law. And to calculate the electric field directly wherever symmetry was applicable, we had Gauss law. In a similar way, in this chapter, to calculate the magnetic field due to a current carrying conductor, we had Biot-Savart law. Right? Now what we have is wherever symmetry is applicable, to find the answer in a lesser time, we have something called as Ampere's circuital law. So here Ampere's circuital law states like this. It states that line integral of B vector dot dl vector is equal to mu naught times the current enclosed. Okay, it is mu naught times the current enclosed. So how is it defined as? It is defined as the line integral of B vector dot dl vector. It is very much similar. See, instead of B vector, you have B vector. Instead of A vector, you have L vector. Instead of 1 by epsilon naught, you have mu naught. Instead of charge, you have current. The only difference is there you did surface integral because you're doing it with respect to area. Here you're doing it with respect to line. So we do line integral. But mathematically, it is still written like this. So the line integral of B vector dot dl vector is equal to mu naught times the charge enclosed by the Gaussian circle. Sorry, charge enclosed. Sorry, I'll come from the beginning. So correction, wait. So it states that the line integral of B vector dot dl vector is equal to mu naught times the current enclosed. So here when I say charge enclosed, no, the charge enclosed is because is charge enclosed by a Gaussian surface. Here the current enclosed is because of something called as Amperian loop. So there we use the word Gaussian surface. Here we use the word Amperian loop. Okay. So this current enclosed is by the Amperian loop, and this is going to be the required mathematical equation. Are you able to understand this? Right. So this is the introduction of Ampere's circuital. Just make a note of it. So now you have to see, we'll calculate the magnetic field due to a straight current carrying conductor. So if I take a straight current carrying conductor of infinite length, right? If I say that the current flowing in this conductor is I, at a distance R, right? At a distance R, right? At a point P, what is going to be the value of magnetic field? Magnetic field at point P will be mu naught I divided by 2 pi R. How did we derive this? So we derived it using the Biot-Savart law, right? If you remember, you had the formula of mu naught I divided by 4 pi R into sine alpha plus sine beta. Then you substituted alpha and beta as 0 and 90 and 90. So you got 2 and it got cancelled. The answer was mu naught I divided by 2 pi R. Is the point clear? Right. Now the question is, can we derive the same thing using Ampere's circuital law? Right. For that, what I will do is, first I will look at the way the conductor is. So here the conductor is carrying the current in the upward direction. So when I curl my fingers are going to go into the plane, and on the other side will come out of the plane. Right. So basically, due to a straight current carrying conductor, the magnetic field lines are going to be circular. They're going to be circular. Right. Now the question is, this is the point at which I'm interested to calculate the magnetic field, for which I'm interested to apply Ampere's circuital law. So what did Ampere's circuital law tell us? The line integral of B dot dl is equal to mu naught into I enclosed. Now the question is, I enclosed is there, no? That I enclosed is within a Amperian loop. Now the question is to consider the Amperian loop for this. So where should I consider the Amperian loop? I'll consider it symmetric with respect to this kind of current flow, where it is going to be a circular Amperian loop. Are you able to understand? And secondly, like how you did, right, how you considered the Gaussian surface, you need to consider the Amperian loop also to pass through the point where the field is expected to be calculated. Am I clear with this? Right? So this is the first step. Now, what is going to be the Amperian loop's radius? R itself, right? Secondly, what I will do is I will take a small element here, and to that element, I will assign the direction as dl. So what we generally do is you will assign the direction of that dl vector, right? So you consider a small element which is dl, and you assign the direction to it in this direction. That is the direction same as that of the magnetic field itself. Right? Because when I say the current is flowing upwards, what is the direction of magnetic field? Is into the plane. So I took dl vector also into the plane. Now I will start applying the Ampere's circuital law. So what did it state? The line integral of B vector dot dl vector is equal to mu naught times the charge enclosed. So when I write this B vector dot dl vector, in this case, B and dl, they both are in the same direction. So when they are in the same direction, the dot product between them will be just the product of their magnitudes. So it will be B into dl is equal to mu naught into I enclosed. Now the question is, mu naught is mu naught only. What is the total current that is enclosed by this Amperian loop? What is the total current flowing through this conductor? It is I. So I'll write I here. Is this point clear? So what did I do? Let's come from the beginning. I took the conductor. I took the point, which is at a distance r. So symmetric with respect to the current carrying conductor, we considered an Amperian loop, and we ensured that the Amperian loop is passing through the point where the field is to be calculated. And on the Amperian loop, you considered a small element dl. And what is the direction you assign to it? You assign the direction of magnetic field itself. After that, you apply the Ampere's circuital law, which says line integral of B dot dl is equal to mu naught into I enclosed. In this case, B and dl are in the same direction. Hence, it will be the product of their magnitudes, which is equal to mu naught into I enclosed. What is the charge? Sorry, what is the current enclosed by the Amperian loop? I. So this is clear. B is a constant at a given distance. Current is same, distance is same. So B is going to be a constant. Can I take the B out of the integral? So if I take B out of the integral, line integral of dl will be equal to mu naught into I. I hope it is clear. So B into, now tell me one thing, listen to this carefully, listen. If I take this dl and add everywhere, right, if I integrate this dl over the Amperian loop, what am I going to get? I'll get the circumference of that Amperian loop. So what is the circumference of it? It is going to be 2 pi r, which is equal to mu naught into I. So what is going to be the value of B? So the value of B in this case is going to be mu naught I divided by 2 pi r itself. Is the point here? So this is going to be the final result. Right? So I can make a note of it. Clear? Right. Shall I proceed? All right. So right. Next, we will see the application of Ampere's circular law. We'll be seeing it for two important devices, out of which one is known as solenoid and the second is known as toroid, T-O-R-O-I-D. Okay, those two are the important applications of this. Right. Now, if you see, what are we interested in this topic? Application of Ampere's circular law for solenoid. So when I take a solenoid, basically what is a solenoid? Observe. So if I take this to be a core is something which is holding the wire. So around this core, I'm going to wind the wire like this. Like what am I doing? I'm just winding the wire like this. Then this wire is what is called, this kind of an arrangement is what is called as a solenoid. So solenoid is basically a helical winding of the wire around a core. Right. So when you observe this on the paper, right? So how will it be is, see, suppose, just a minute. See, for those who are online, I'm just showing you how it looks like. Okay. Now, if you observe it on a paper, let's say that the current in this conductor is flowing from the bottom to the top. So at the top, how is it entering? Is it entering into the plane or is it out of the plane? So it is entering into the plane, and at the bottom, it will be out of the plane. These are the 2 points that you need to keep in your mind. So when you see from this side, how does it look like? It looks like a circle. Whereas when you look from this side, it will look like some other shape. I'll draw that shape and show you. So basically, this is the cross-sectional area of a cylinder. Right? When you see from this side, you're able to see the circular part. Whereas when you see from this side, are you able to see the complete cylinder? You're only able to see the front part of it. No, when the front part is projected on the paper, it has a different perspective. Okay, observe how it is going to look like. Right. Now, if you see, basically, how is a solenoid going to look like? Let's say there is a core onto which there is a wire that is wound like this. So in the example that I considered, I'm saying that the current is in this direction. The way I showed you, the current is in this direction, so that at the top, the direction of current is into the plane, and at the bottom, the direction of current is out of the plane. Clear with this? Right. Now, what we need to do here is, we need to consider the Ampere circuital law and solve this problem. Right. So that's what the problem statement is. We need to find what is the magnetic field generated due to this kind of a circuit called as the solenoid. Right. For that, observe, this is cylindrical, right? When you take a cylinder and project it on a two-dimensional plane, on a two-dimensional surface, a cylinder will look like a rectangle. So cylinder projected, a three-dimensional shape projected on a two-dimensional surface is going to be a rectangle. Okay. So when you take this rectangle, right, when you take this rectangle, at the top, the current is going to be into the plane, and at the bottom, the current is going to be out of the plane. So here, into and dot represents what? They represent the direction of current. So don't get confused thinking that it represents the direction of magnetic field. No. Am I clear with this? Right. Now let me take the length of the solenoid to be L. So what did I do? I took the length of the solenoid to be L, and I took the number of turns in the solenoid to be capital N. Right. So can I define a parameter called as capital N divided by L? So what is this basically? It is the number of turns per unit length. So number of turns per unit length. This is represented as small n. So remember, in physics, always remember, in physics, capital N is used for number of turns, small n is used for number density. So here, what is the number density it is representing? It is the number of turns per unit length. Am I clear with this? Right. Now, if you see, what is that we need to do? We need to apply the Ampere's circuital law. So for Ampere's circuital law to be applied, I need to consider an Amperian loop symmetric with respect to the current distribution. Symmetric with respect to current distribution. So if I look at this rectangular shape, what I will do is I'll consider an Amperian loop in such a way that it is going to be a rectangle, because for rectangle, then other symmetric shape I can think of is another rectangle only. No? I'll consider the rectangle in such a way that the half portion is inside the solenoid and half portion is outside the solenoid. Right? So half portion is going to be out of the solenoid. Now, if I take this length to be, okay, suppose I take this length to be small l, right, and I take the number of turns to be n dash, okay, or else I'll do one thing. I'll take the number of turns to be n dash, and the length of this portion to be l dash. Okay, so that here one thing that is there, n dash divided by l dash, what does this represent? This is also going to be number of turns in this length, number of turns per unit length, where this value you should not write it as small n dash, rather it is small n only. Means number of turns can change, length can change, but the ratio of those two quantities will always be a constant. That is how the windings are. The windings are equally spaced. How they play? The windings are equally spaced. Am I clear with this? So the number density is going to be the same, right? So what do we need to do? We need to calculate the magnetic field due to this shape. So how to proceed? So I've considered the Amperian loop also. We have considered the Amperian loop. Let me say this is A, B, C, D. Okay, the loop's name is A, B, C, D. Now listen to this carefully. If the current is into the plane, what is going to be the direction of magnetic field? So if I take my thumb and place it in the direction of current at the top, so when I place it in the direction of current at the top, when I curl my fingers, the magnetic field is, look at my fingers. The magnetic field is in this direction. Is the point clear? So magnetic field is going to be in this direction, right? Now, if you observe, out of the surfaces AB, BC, CD, and DA, what is going to be the angle between the magnetic field and AD? What is the magnetic field between B and AD? It is 90. So AD will not participate in the Ampere circuital law. So what is the angle between B vector and AB? 0. So that will participate. What is the angle between B vector and BC? Again, BC and B vector. BC and B vector. They both are perpendicular to each other. Now, what about B vector and CD? 0. But one point that you need to consider here is when I say the solenoid here, right? In your physics, the solenoid that we consider is a long solenoid. When I say long solenoid, the length of that solenoid is going to be very large compared to its thickness, right? So length is going to be large compared to its thickness. So that's what is meant by a long solenoid. So by default in physics, whenever they say solenoid, they're referring only to a long solenoid. So for a long solenoid, what will happen is the magnetic field outside the solenoid will be 0. So magnetic field outside the solenoid will be 0. So the magnetic field for a long solenoid will exist only within the solenoid itself. So which is the only portion of the Amperian loop which is going to participate in the, it is AB. So what I will do is line integral of B vector dot dl vector is equal to mu naught into the charge enclosed by whom? By the Amperian loop. Right. So here B vector and L vector are in the same direction. So what is the length of AB? Let's see. So here I will write it as AB. I hope you're able to understand this. Okay, to be more specific, I'll write it as BA because I told you, DL vector generally will consider it in the direction of magnetic field itself. I'll write it as BA. So what will be the angle between them? 0. So what will get multiplied? Only the magnitudes. So the line integral of BA, which is going to be B into DL, will be equal to mu naught into. So what I need to calculate is the current enclosed. Listen to this carefully. Okay, listen to this carefully. So what is going to be the value of current that is enclosed in this surface? What will be the current that will get enclosed in this region? So tell me, in this region between A to B, how many windings are there? The region between A to B, how many windings are there? N dash windings are there, right? So each winding carries a current of I. How much is each winding carrying? I. So N dash winding will carry a current of N dash I. Got it? So the total current that is enclosed here is going to be N dash times I. Make sense? Am I clear till this point? So N dash into I. So B can be taken out of the integral. B into the line integral of DL from B to A is going to be how much? I'll first finish this. B into, what is the line integral of DL? So what is the length of AB? Length of AB is L dash. So capital B into L dash is equal to, what is there on the right hand side? It is going to be mu naught into N dash into I. So what will be the value of B? It will be mu naught into N dash divided by L dash into I. What is N dash by L dash? Small n. So this will be equal to mu naught times N into I. So the magnetic field due to a long solenoid is going to be mu naught into N into I, and this value is going to be the magnetic field which is present at the center of the solenoid. Right? This value is to be remembered. It is a very, very important one. We'll use it in the next chapter also. So what is going to be the value? It will be mu naught into small n into I. Am I clear with this? Right? Okay. Number of bindings, no? When it comes to a coil, like they are connected in series. அதனால தான் இப்ப ஒண்ணும் இல்ல. See, ஒரு circular current loop எடுத்துக்கிட்டேன்னு வச்சுக்கோ. What is the magnetic field due to a circular loop at the center? Mu naught I divided by center of the circular current carrying conductor. Pi வராது. நான் இந்த பாயிண்ட் சொன்ன வாங்கிட்டேன். இந்த மிஸ்டேக் பண்ணுவீங்கன்னு எனக்கு தெரியும். I told mu naught I divided by 2. Pi வராது. It's just mu naught I divided by 2a. நோட்ஸ் இதே நோட்ஸ் எழுதுறியா இல்ல மாத்தி மாத்தி எழுதுறேன்? அந்த நோட்ல இருக்கும் பாரு. இதே நோட்ஸாடா? அதே நோட்ஸா? அதுல போனப்ப when I explained about circular current carrying conductor, I derived a value இல்ல mu naught I by 2a இருக்கா பாரு. அந்த ஆக்சிஸ் வச்சு ஒன்று பண்ணியிருப்போம், ஞாபகம் இருக்கா? ஆக்சிஸ்ல பண்ணிட்டு ஸ்பெஷல் கேஸ்ன்னு போட்டிருப்பேன். பட் இது பாரு mu naught I by 2a. நான் இங்க மென்ஷன் பண்ண கூட இவங்க கூட எழுதல. I asked you to write this point. So when it comes as mu naught I by 2a, people will get confused. இங்க 2 pi போட்டுருவாங்க by default. ஏன்? Because when we think of circle, circumference ஞாபகம் வந்துரும் நம்ம. So we by mistake will put it as 2 pi a. But circle வராது. இப்ப நீ கூட அதே தப்பு தான் பண்ண. That happens. I've seen that mistake. அதனால தான் ஸ்ட்ரெஸ் பண்ணி இப்ப எழுதிக்கோ. இங்க pi வராது. Okay? So for circle you will not get pi, whereas for a இல்ல வேற எங்கேயாவது எழுதிருக்கேன் நீ. இங்க கூட ஆன்சர் 6 விட்டு. Okay. So that will not come. So if the mu naught I divided by 2a because of one turn. If n turns இருந்தா அதே லாஜிக் தான். Because each turn is in series with the next one. அதாவது n times a ஏன் ஆகுதுன்னா ஆம்பிளிஃபை ஆகுது. இப்போ ஒரு லூப் வந்து இட்ஸ் நாட் லைக் சீரீஸ்ன்னு சொல்றதுனால யூ கேன் ஆஸ்க் மீ கொஸ்டின் சார் அப்ப ஐ தானே இருக்கணும். அப்படி கிடையாது. இப்போ ஒரு வைண்டிங் இருந்ததுன்னா ஐ ஜென்ரேட் ஆகுதுன்னா n வைண்டிங்ஸ் இருக்கிறப்ப the intensity is getting amplified. அதனால தான் n dash I நம்ம போட்டு. புரியுதா? So here you should not take the resistors into consideration. அப்படி பார்க்க கூடாது. சென்டர்ல மட்டும்தான். ஏன்னா இது லாங் சாலினாய்டுக்கு மட்டும்டா. லாங் சாலினாய்டுக்கு ஐம் டெல்லிங். இல்ல இப்படி இருக்காது. எண்ட்ஸ்ல வந்து மாறும். இட் வில் பி half. அது உங்க சிலபஸ்ல இல்லை, அதனால யூ வில் நாட் வரி அபவுட் இட். எண்ட்ஸ்ல மாறும். ஸோ இது சென்டர்ல வந்து வரும்போது இட் இஸ் mu naught ni. எண்ட்ஸ்ல வந்து mu naught ni by 2ன்னு வரும். இதோட half வேல்யூ இருக்கும். அதுவும் சொல்லலாம். Yeah, that is one of the reasons. And moreover, some magnetic field will escape. புரியுதாடா? So you asked me a question of why did I take n dash I. I hope you also got the answer. Why is it coming? Can you just tell me? ஒரு வைண்டிங் இருந்தா கரண்ட் I. இப்போ n வைண்டிங்ஸ்னால என்ன ஆகும்? மேக்னெட்டிக் ஃபீல்ட் will get intensified. இப்போ இதுக்கு எக்ஸாம்பிள் என்னன்னா, நேற்று ஒரு கான்செப்ட் டிஸ்கஸ் பண்ணோம் கேல்வனோமீட்டர்ல. சென்சிட்டிவிட்டியை பத்தி இப்போ நான் சொல்லியிருப்பேன், போய் பாருங்க. What did I tell there? The sensitivity factors on which sensitivity of a galvanometer depends on. What is the first thing you are able to see? 4 பாயிண்ட்ல டிபெண்ட் ஆகும். என்னது? N, B, A, K. So number of turns மேல டிபெண்ட் ஆகுதா? So number of turns இன்க்ரீஸ் பண்ண என்ன ஆகும்? அதோட சென்சிட்டிவிட்டி அதிகமாகும். ஸோ அதனால இந்த சாப்டர் பொறுத்த வரைக்கும், இந்த சாப்டர்னு இல்லை, ஜென்ரலி சி இஃப் யூ லுக் அட் த ரியல் டைம் அப்ளிகேஷன், இதுதான் திருப்பி ஃபேன்ல ஏசிலலாம் யூஸ் காயில்ஸ், தே டோன்ட் யூஸ் லூப்ஸ். அதெல்லாம் எதுக்கான இந்த இன்டென்சிஃபை பண்றதுக்காக. இதுக்குள்ளெல்லாம் இருக்கும்டா, நீங்க எப்பயோ பார்த்துருக்கீங்களா ரிப்பேர் பண்றப்ப? நெக்ஸ்ட் டைம் அப்சர்வ் பண்ணுங்க, காயிலா இருக்கும் உள்ள. ஏசி ஆல்சோ அப்சர்வ் whenever they're doing a cleaning or a repair work, coils இருக்கும். All works on this case only, magnetic field and magnetic induction. How deep up over, but yeah, this is the outline. Purida. Okay. So whatever we derived here is for a long solenoid. Okay. So does anyone have textbook? It's a revised one, no? Revised new one? Older. Okay. Revised. So I'll just tell the name of the topic. You tell me whether we have discussed or not. Introduction, obviously, yes, we have completed. So we understood what is Lorentz force, right? We discussed it. So magnetic force on a current carrying conductor, we calculated BIL sin theta. Right. Then we saw motion of a charged particle in magnetic field. When theta is equal to 0, you will get a straight line. When theta is equal to 90, you will get a circular path. When theta is anything other than 0, 90 or 180, you will get helical path. I discussed two concepts there. One is pitch and the next is how much is the radius of it. Radius is equal to mv sin theta divided by qb. Nyaborka. Adhe mari pitch la you will get a constant. 2 pi mv cos theta divided by q into b. Right. So that we have discussed. Then we have discussed Biot-Savart law. Right. So we have seen the application of Biot-Savart law. What is it? See in your textbook, right? The first derivation that I gave you is not there. Which one? The state current carrying conductor, sin alpha plus sin beta. Textbook, you cannot find it. Okay, I gave that for a specific reason because sometimes they'll ask you problems based on it. You might get marks, you might not get marks. That's a different story. But if at all that comes, I don't want you to struggle. So another practice in my test I'll ask. Okay. So I've discussed about straight current carrying conductor and circular also on the axis of it. Then we saw Ampere's circuital law. For Ampere's circuital law, we have calculated for solenoid. So one concept that is left out is toroid, which I told you. Right. Okay. One concept. The toroid is deleted actually. Correct. Revised book. Toroid is deleted. And one concept force between two parallel current carrying conductors explain pannu. After that, torque experienced by current carrying loop na solita NIBA sin theta. 2 days back we discussed. So at the base panni we saw the application also. What was it? Moving coil galvanometer. Moving coil galvanometer la current sensitivity solita, figure of merit solita, voltage sensitivity I explained. Right? Then I also told you how to convert a galvanometer to an ammeter and a voltmeter. So the last concept that is left out is force between two parallel current carrying conductors. With that, we are done with this chapter. So the next thing that I'm going to focus is more of problems. Is that clear? This chapter alone, I want to solve few more problems because it is slightly considered to be lengthy and tough. Tough actually, it's lengthy. So too many concepts are confused. Okay, I'll help you solve it. Don't worry. Am I clear, guys? Right. So let me just change the topic alone. No? Give me a minute. So what did I say? The topic left out. Those who are online, are you able to understand?
Sure.
A lot of discussions are happening here. 1 minute. No? Bhaskar, yaru vandirukanga paru. Pat. So toroid is deleted. So what we'll see is, what is the topic I told you? Force between two parallel current, spelling correct paranga. Current carrying conductors, all fine. So force between two parallel current carrying conductors. No spelling mistake, no? Yeah. So shall we get started with that?
Yes, sir.
Those who are online, are you able to see the screen?
Yes, sir.
Okay. See, this is a very simple concept. Okay. But there is something important that you need to observe. There are many problems asked based on this. I'll tell you what you're supposed to observe. Right. Yeah. So the topic that we are going to discuss now is force between two parallel current carrying conductors. As the name suggests, what is that you have? What is the subject here? You have two parallel current carrying conductors. So parallel means obviously they're supposed to be straight, right? Two parallel current carrying conductors where let's say the current in both the conductors is going to be I1 and I2, and we consider them to be long conductors. You know what is the meaning of long, right? They're considered to be infinitely long. And let's say the distance of separation between them is small d. Okay. Now, what we need to understand is there something going to exist between them? How are they going to interact with each other? What do I mean by interact? Whether they will be able to apply force on each other or torque on each other. So obviously torque will not come here because it's not a closed shape. So the only thing that is possible is force. So that's why the name of the topic is force between two parallel current carrying conductors. Now thinking about this, see, if you come from the beginning of this chapter, we know one thing. We know two things actually. One is a current carrying conductor can produce magnetic field. Listen to this carefully. What is the story? The story is current carrying conductor can generate magnetic field. That is the first step. So what is the meaning of this? This current carrying conductor can generate a magnetic field around. This current carrying conductor can generate a magnetic field around. Okay. Secondly, so this is the first part of the story. The second part is current carrying conductor placed in magnetic field experiences force. You know this? So what is the force experienced by it? It is going to be BIL sin theta, where theta is going to be the angle between magnetic field and the L vector. I into L cross B. Am I right? Now, current carrying conductor can generate magnetic field. Here, due to a long current carrying conductor, what is the magnetic field generated at a distance d? It is going to be mu naught I divided by 2 pi d. So these two are the mathematical expressions that we are going to use to calculate the force. Am I clear with this? Okay. Just give me that. Okay. Now, if I take this conductor to be 1 and I take this conductor to be 2. Okay. Now, I'll go step by step. Tell me, what is the magnetic field generated due to the first conductor near the second conductor? So, what is the magnetic field generated due to the first conductor near the second conductor or on the second conductor itself? It is going to be mu naught I I1, because the current in it is I1. Mu naught I1 divided by 2 pi into d. Makes sense? Now, the next question is, if I write it in the vector form, what is going to be the direction in which it is going to experience force? It will be into the plane. So it will be into the plane. So since it is into the plane, I'll put a mark like this. So remember, into the plane is going to be the magnetic field due to the first conductor. Now, what I'm going to do is, see, since this is of infinite length, right? Since this is of infinite length, what I will do is, since I know force can be calculated only on a part of the conductor, because it is having L, right? I will take a small portion L on the second conductor. Make sense? What am I doing? I'm taking a small portion L on the second conductor because I need to apply this formula. I need to know what that L is. If I put infinity, I will get the force as infinity. It doesn't make sense. So I'm calculating what is the force experienced by a portion of the second conductor. Due to whom? Due to the magnetic field produced by the first conductor. Force experienced by second conductor due to the magnetic field generated by the first conductor. So observe this. I am writing this as, first observe. Everybody observe. Observe. So F is there. I will put the subscript as 2-1. So what is the meaning of this? Force experienced by the second conductor due to the magnetic field from the first conductor. Right? This is going to be equal to how much? It is going to be B into I into L sine theta. Here, what is the value of theta? Current is in this direction. Magnetic field is in this direction. So when I turn and see it like this. So current is upward. Magnetic field is into the plane. I keep it like this. So when I turn and show it to you, what is the angle between them? 90. So theta is going to be 90. So in this case, I will apply the formula V into I into L. So here, what I'm going to do is, I will write the magnetic field generated due to the first conductor. Current due to the second conductor. And length of the portion of the second conductor. Okay, L2. That is this portion. Did you understand the notations? Am I clear? So what is the value of B1? Take it, substitute it there. I'm only writing magnitude if you observe clearly. Right? Only the magnitude. So it is going to be mu naught I1, the whole divided by 2 pi into D into what is the value of I2? I2 only, small I2, into the length of the portion is going to be capital L. So this is F21. Now what I will do is I'll write it in the vector form. Right? When I write it in the vector form now, tell me, using the Fleming's left-hand rule, tell me what is going to be the direction in which this second conductor experiences force. So first, take your forefinger, put it in the direction of field. Extend the second finger and adjust it in the direction of current. And extend the thumb. So thumb gives you the direction of force. So thumb is going to be in the leftward direction. Having said this, the force is going to be in this direction. So F21 is in the leftward direction. Makes sense? Am I clear? So F21 is equal to mu naught I1 I2 by 2 pi D into L. So bring that L to the left hand side. What will you get? You will get F21 vector divided by L is equal to mu naught I1 I2 divided by 2 pi into D. In which direction? In the leftward direction, leftward, LW. Clear with this? Right? No, wait. So this is not the force actually. This is the force per unit length, right? So whenever they ask you the question, right? If they ask you what is the force experienced by the second conductor, they need to give you the length of the portion of the second conductor. Only then you will be able to calculate the absolute force. If the length is not given and they still consider it as a long conductor, you will not be able to calculate the force. Rather, you can only calculate force per unit length. You will only be able to calculate. So that is why be very careful with the question. If they ask you force, they need to give you this L value so that you will take this L and multiply on the other side to get the final result. If that is not given, then you can only calculate force per unit length. So F21 divided by L is going to be the force per unit length of the second conductor on the second conductor due to the magnetic field produced by the first conductor. Now, all that I need to do is, see, I calculated this value. Remember this mu naught I1 I2 divided by 2 pi D. Now I am exactly going to do the reverse scenario. Means I'll calculate what is the value of F12 by L. I'll take the same length L. Observe, see what is going to happen. So when I take So if I take the same scenario, but this time it is going to be in the reverse. I1 here, I2 here, the distance of separation taken to be D. Okay. Now, if you observe, at this point, what is the magnetic field generated by the second conductor? It is going to be mu naught I 2 divided by 2 pi into the same distance D. But this time, in which direction is it going to be? It will be outward, right? So when it is going to be outward, you will put a dot and a circle around it, and this is how it is written. So here it is going to be dot and it is in the outward direction. Now the question is, what is the force experienced by the first conductor due to the magnetic field produced by the second? It is BIL. So B magnetic field is due to the second conductor. Current is due to the first conductor. Then what should I consider? I will take a small portion of the same length L that I considered on the other side. So it is going to be capital L. Now what is going to be the angle between them? This is L and this is the direction of magnetic field. Right? When you turn and see, it is going to be 90 degrees. So again, sine 90. So I need not worry about this. Right? It is going to be sine 90. So B2 is how much? Mu naught I2 divided by 2 pi D into I1 is I1 only. Length is capital L. So this is going to be F21. Now I will find the direction. What is the direction of field? There is the direction of field. Direction of current is upward, and extend my thumb. The thumb is going to be in the rightward direction. So force experienced by the first conductor due to second, F12 is going to be in the rightward direction. Are you able to understand? Oh, sorry. So correction here it is F12. Right? So force experienced by the first conductor due to the magnetic field from second is going to be mu naught I2 I1 into L divided by 2 pi D. So what I'll do is I'll bring the L to the left hand side, right? So when I bring the L to the left hand side, it will become the force per unit length, which is also going to be equal to mu naught times I1 I2 divided by 2 pi D, which is going to be in the rightward direction. Now the question is, in the same scenario, what was the direction of F12? It is to the right. And what is the direction of F21? It is to the left. Listen to this very carefully. Listen to this carefully. Questions are framed based on this only. By looking at the diagram, you should be able to tell. Okay, listen. Here the currents are flowing in the same direction, right? So when currents are flowing in the same direction, right, the conductors attract each other. They attract each other. Whereas if the currents are in opposite direction, then the conductors repel each other. So are you able to understand? So that is F12 would have been in this direction, F21 would have been in this direction where the currents were in opposite direction. You can try that and see. So all that you need to do is apply the same logic. First, calculate the magnetic field due to 1 at point 2, and then calculate the force experienced by the second due to 1, and vice versa. Is the point clear? So this is a very, very, very important conclusion. Next time, by looking at the diagram, you should be in a position to tell whether they are going to attract or repel. Is that clear? So this is all about the concept of force between two parallel current carrying conductors. What did you calculate? You calculated the force per unit length. Is it clear? It follows Newton's third law. Yeah, that also it can. But here there is no external force law. It is happening due to the system itself. This is generated either or part of the system, either or part of the system. It is creating a force there, and this is creating a force. It's happening internally. So just to conclude, we are done with this chapter. Okay. So you'll be getting an assignment this week. Solve them. Solve all the problems. Okay. And Monday and Tuesday we'll try to discuss them, and on Wednesday I'll start the next chapter. That is the 5th chapter, magnetism and its matter. So that is very small, maximum 3 days at all time, and that's more of theory. Okay, I'll go to the concept of electromagnetic induction. That will also take only 3 weeks. Faster. Again, a break will come in near ray optics and wave optics. Various chapters. Everything is 2 classes. 11, 12, 13, 14. Only 2 classes. So as I told you, by October we'll complete it and we'll have more revisions, more of problems. Okay, this is July, right? August, September, we can complete it comfortably. Okay. So make a note of this. On the previous slide. The problem solve பண்ணிருந்தா. See, after this we can wind up. If you have any doubts, you can ask me, or else if you have completed, you can leave. Those are online also, the same thing. Okay. If you have any doubts, you can ask me, or else you can leave. Oh, sorry, give our instant. Okay. Yeah, in the point P, இது 45 degrees. இது எவ்வளோ? இது ஆர்னு எடுத்துக்கிட்டேன்னு வச்சுக்கோ. இது எக்ஸ்ன்னு எடுத்தேன்னா x by r is equal to sin 45. So this is r by root 2, this is r by root 2. Correct?
Distance.
இது இன்னும் முடிக்கலாம். இதோட ஐயா இதுவும் ஐயா. அப்போ இது ஃபர்ஸ்ட் எடுக்கிறேன், செகண்ட் எடுக்கிறேன். b1 will be mu naught I by r by root 2. b2 will be mu naught I by r by root 2. Right. So they both are. So due to this it is into the plane, due to this also it is into the plane. So when you add them vectorially, you can get mu naught I divided by r into root 2 plus root 2, it should be 2 root 2. Option is clear. அப்ப நீ என்ன பண்றன்னா, it is closer to the conductor. இப்படி எடுத்தா கூட can still take this r by root 2 to be one of the parameters. Okay, இது எப்படி எக்ஸ்பெக்ட் பண்றாங்கன்னா, this you can take it as 45 degrees. So mu naught I divided by 4 pi r. அதுல வைஃபை அதுல வைஃபை கிளிக் பண்ணேன். இன்னும் ஆகல, ஆஃப் ஆகல. வைஃபை கிளிக் பண்ணி எஸ் கொடுத்துட்டு ஆனா இங்க வருது எனக்கு. ஆஃப் ஆயிடுச்சு. ஸோ மியூ நாட் ஐ பை 4 pi r into sin alpha plus sin beta. ஸோ sin alpha திருப்பி 45 degrees தான் வரும். sin beta வந்து 0 ஆயிடும். அதேதான் வருதுடா. ஆப்ஷன் எது தப்பா இருக்கு. The printing mistake. நான் மிஸ் பண்றேன்னு தெரியல. ஒரு வாட்டி உங்க டீச்சரை கேட்டு பார்த்தியா? ஒரு வாட்டி கேட்டு பாரு. எனக்கு தெரிஞ்சு நான் எதுவும் மிஸ் பண்ணல. ஏன்னா இது இந்த டைரக்ஷன்ல இருக்கு, இதுவும் உள்ள இருக்கு, இதுவும் உள்ள இருக்கு. ஸோ தேர் இஸ் நத்திங் லைக் ஐ நீட் டு அப்ளை parallelogram law of vectors எதாவது பண்ணலான்னு பார்த்தா அதுவும் தேவையில்லை. ஆக்சுவலா சிம்பிள் தான். இல்ல சேமா தான் எடுக்கணும்.
இந்த பாயிண்ட் இந்த பாயிண்ட் திரும்ப எந்த கண்டக்டர் எடுக்குமோ திரும்ப இந்த பாயிண்ட் எடுக்கணுமான்றது.
இல்ல அது தேவையில்ல. பாயிண்ட் எடுக்க மாட்டேன், எப்பவுமே கண்டக்டர் தான் எடுக்கும். You don't take point and calculate it. So those who are online, are you done? I think they would have left.
Yes, sir.
Yeah. So there are no doubts, you can wind up. No questions? Divya and Harini, no questions, no?
No, sir.
Okay, then we'll wind up.
No, sir.
Yeah.
Thank you, sir.